have a sample size of 4. 2 of them have thick atmospheres, 2 of them don't. Why is that? Is it also true for other terrestrial planets? And in particular, is it true for terrestrial planets orbiting M-dwarfs? So we know that most of the terrestrial planets in the galaxy are actually orbiting stars that are much smaller than the sun. And this is kind of a blessing and a curse. On the one hand, the smaller the star is, the easier it is to characterize the planet because we're always making these differential measurements. But on the other hand, M-dwarfs pose some problems for the survival of atmospheres on rocky planets. In particular, they are very bright in the ultraviolet for the first billion years of their lives, and that can contribute to massive amounts of photoevaporation. So you can photoevaporate many Earth oceans worth of water. On a tidally locked planet, you can also have the atmosphere freeze out on the night side. This is technically called atmospheric collapse. I call it the snow cone problem, where you have a frozen ice side and then a bare rocky side. Okay. So far, there have been several attempts to study the atmospheres of terrestrial planets around M-dwarfs using the canonical technique of transmission spectroscopy, where the planet passes in front of the star. In all cases, the results have shown flat spectra that are precise enough to rule out hydrogen-rich atmospheres on the planets. And that jives with expectations from theory. It's really hard to hold on to a hydrogen-rich atmosphere on a terrestrial planet. But the data are not precise enough yet to be able to say whether there is a high mean molecular weight atmosphere. If you have heavier molecules, it shrinks the size of your atmosphere by about a factor of 10 compared to a hydrogen-rich composition. And there could also be clouds in the atmosphere, so it's been inconclusive so far whether these planets have atmospheres or not. I'm impatient, and so I wanted to see whether I could address this question now with any facilities we currently have access to. And so I, together with Avi, developed a different idea where if you observe the thermal phase curve of a planet, you can measure its climate. And if you detect a large variation in temperature between the day side and the night side of the planet, that means that there cannot be a thick atmosphere that would redistribute heat from the day side to the night side. And so if you measure large amplitude phase curve, that suggests there's no atmosphere. If you measure a small amplitude phase curve, thick atmosphere. Up until a year ago, there were no planets for which this measurement was possible. But thanks to the TESS mission, which recently launched and is discovering transiting planets around the nearest and brightest stars in the sky, we found a terrestrial planet orbiting a nearby M-dwarf. And this is a special one because it has a really short orbital period, just 11 hours. So the equilibrium temperature of the planet is about 1,000 Kelvin. That's exciting because it's hot enough to detect the thermal emission, but not so hot that it would have necessarily lost its atmosphere. So you could have a stable oxygen-rich atmosphere, CO2-rich atmosphere on this planet. And so I stayed up all night and wrote a Spitzer DBT proposal for 100 hours of observing time to get 9 continuous orbits of the planet in the infrared at 4.5 microns. You guys have all seen this already, so I'll just go right to it. There it is, ta-da! Okay, so this is a pretty big amplitude, right? The night side temperature is consistent with 0. The day side is about 1100 Kelvin. There's no offset in peak brightness that could occur if there's an atmosphere circulating heat around. It's looking an awful lot like a bare rock. Now, I wanted to make sure we did our homework on this, and so we asked the question, what kind of atmospheres could you put on this planet that are consistent with what we measured? And so this is I put together a dream team of theorists. This is work from Daniel Cole and Caroline Morley, where we compared the measured dayside eclipse depth, that's the black line with the gray bar, to predictions from theoretical models for different atmospheric compositions. And so we considered mainly oxygen and CO2 mixtures based on the expected evolution of an atmosphere at temperatures this hot. And you can see that for higher surface pressures, the expected eclipse depth is lower because the day side cools off as you circulate heat to the night side. So based on these models, we found that we could rule out surface pressures greater than 10 bars at 3 sigma confidence. So Venus-like atmospheric composition is ruled out. And our second question was, so if you can't have a thick atmosphere, is a thin atmosphere stable over the planet's lifetime? And so this is work from Laura Schaefer, where she modeled the planet as having an initial envelope made of water predominantly, and evolved it over time. This is the UV brightness of the star during its bright pre-made sequence phase for about 1 billion years. And in her model, the water can photodissociate, the hydrogen is light, it easily escapes to space, can also dissolve in the rock of the surface. And what you're left over with is an oxygen-dominated atmosphere, molecular oxygen. And what we found is that for you either end up with one of two situations. Either your atmosphere is totally lost, or you have a thick envelope greater than 10 bars of oxygen. So we ruled that out based on the data. And there's a tiny, tiny wedge of parameter space here where you can have a thin atmosphere that is stable, but it's quite a bit lower UV brightness than is expected for an M dwarf. So this red dot here is 80 Leo, which is a good proxy for the host star in the system. And so the star would have had to have been very faint in the UV compared to what we expect to get a stable atmosphere. In addition to this, we also expect about 1 to 10 bars of atmosphere to be eroded by the stellar wind over the planet's lifetime. And so most likely, there is no atmosphere on this planet, and we're looking at a bare rocky surface. And that's really cool. Rocks are so interesting. So I should note that ExoCup is going on right now on Twitter, and LHS3844b, this planet, is a contender. I think you have like 20 more minutes to vote for LHS3844b. Take out your phones. Because this is so cool. If we're seeing the surface of a rocky exoplanet, we can ask the question, what kind of rock are we looking at? And based on the measured secondary eclipse depth, right here, we can already begin to rule out certain kinds of rock. So it's so hot that the surface has to be quite dark. So the best fit compositions are basaltic in nature, which could form from cooling rock from volcanic activity, similar to the surface of Mercury or the Moon. Okay, so this is all awesome. But I feel like I started out with some questions and I may have left you with more questions than I started with. So I asked, is there a universal trend in the atmospheric composition of planets with planet mass? I gave you one data point, there's more coming. Where is the dividing line between rocky and gaseous planets? For this, we need to start studying the smaller planets. What is the 3D structure of planetary atmospheres? We know that they're 3D, and we've seen the very first glimpses of what that might look like. What's going on with clouds? And perhaps most excitingly, how often do terrestrial planets hold on to their atmospheres? And if they do hold on, what are they made out of? Okay, so in the last couple of minutes, last 15 minutes or so, I want to talk about the landscape of exoplanet atmosphere characterization over the next 10 years. And here's a rough timeline. So here we are now. All of the best planets in the sky to characterize are being discovered in droves by TESS. More to come from future surveys. We're doing the first reconnaissance of what their properties are using Hubble, using Spitzer. And in the mid-2020, early to mid-2020s, there are a whole bunch of new facilities coming online that will each have revolutionary new capability for studying planetary atmospheres. And so I'll go through each of these in some detail. JDBC is a huge one. I like to say that it is 10,000 times better than Hubble, so I'll give you all my factors of 10. 10 times better, 10 times more collecting area. 10 times wider wavelength coverage, so we can really go into the infrared, where all of my favorite molecules have beautiful spectral features. Pointing stability is also about 10 times better, and that is super important from the technical standpoint of actually making a successful measurement. And the spectral resolution is also better, so we can really see the shape of spectral features, and there's a lot of information encoded there. To give you a flavor of what we expect JDBC data to look like for exoplanet atmospheres, here are some simulated spectra for an early release science program that was awarded to the transiting exoplanet community. One pillar of this program is to observe a panchromatic transmission spectrum of a hot Jupiter. The yellow points are showing what we have measured with Hubble. You can see that not only is the precision way better, but we have access to all of these other features. So we see different molecules, CO2, CO, CH4. You can really see the shape of the spectral feature. And the expectation there is that we'll be able to measure the chemical composition of the planet within a sort of